Hi, it's Mrs. Westmoreland, and this is a quick explanation for finding the pH of a salt. So let's say, for example, that I had prepared a solution of sodium bicarbonate. And I know that sodium bicarbonate is made up of sodium ions and bicarbonate ions. And so sodium ion, since it is the cation of a strong base, would be neutral in solution. It doesn't have any acid or basic properties. But the bicarbonate ion, since it is the anion of a weak acid, it would have acid-base properties. It itself is a conjugate base. So, as you recall from ChemGuy, the neutral ions are the group 1 and 2 cations. So those would be the cations of the strong bases. And then they are the anions of the strong acids except sulfate. So chloride, bromide, iodide, nitrate, and perchlorate. So if we have a salt that has either acidic or basic properties, it will be the cations that would have acid properties, since they would be conjugate acids of weak bases. So you can see in this example, if this is my conjugate base, if this was part of a salt, then it's going to be the conjugate acid of a weak base. Then this would be the proton donor. So when it interacts with water, it could donate the proton to water, and that would form hydronium. So that's why this salt is acidic. We have a little bit of extra hydronium in the solution. And then you would get a small amount of the conjugate base. The anions of the salts are going to be the ones that have basic properties. So since this anion, A- would be the conjugate base of a weak acid, it's going to be a proton acceptor, take a proton off of the water and form a tiny bit of its conjugate acid and also a small amount of hydroxide ion, enough to change the pH from 7. So since my salt has a basic anion, the bicarbonate ion is going to be my base. So when it interacts with water, it's going to be the proton acceptor. Proton is going to be transferred from water to bicarbonate, forming carbonic acid and a little bit of hydroxide ion. So this essentially is the R of my rice table to calculate the pH of the salt. So in your lab, you prepared a solution of 0.25 molarity of your salt. So if you have 0.25 molarity sodium bicarbonate, then you're going to have 0.25 molarity sodium ion and 0.25 molarity bicarbonate ion. So that's my initial concentration. So the change would just be minus x plus x plus x using this dissociation. And therefore, at equilibrium, we would have 0.25 minus x for the concentration of the base, the bicarbonate ion, and we can neglect x. And we'd have x concentrations of both the carbonic acid and the hydroxide. So this is a base dissociation, so this is a Kb problem. So I can write the Kb expression using products over reactants. And now I have to find a value for Kb to plug in. Now, the relationship that is on your formula chart is that Kb times Ka is equal to Kw. Kw being the constant of 1 times 10 to the minus 14. So if I want to know the Kb of bicarbonate, I have to solve for it. It's not really something that could easily be looked up on a table. What could be easily looked up on a table and is found in your lab packet is the Ka of this thing, of the conjugate acid. So the Ka of carbonic acid times the Kb of the bicarbonate ion is equal to Kw. So if I know from the packet what the Ka of this is, I can solve for the Kb of the bicarbonate ion, which I get is 2.4 times 10 to the minus 8. And then I just substitute into my Ka expression, Kb expression. So this is the value of Kb. And then that's going to be set equal to x squared over 0.25 because I'm neglecting x. So I solve for x. Now I need to understand from my KB equation that the x is equal to the hydroxide ion concentration at equilibrium. So if I want to know the pH of this salt, I would just take 14 minus the negative log of x, and I get, in this case, 9.89, which confirms what I suspected to be true, that this salt, which would be the product of a strong base reacting with a weak acid, would have a basic pH. Thanks for listening. See you in class.